to tell you about a project that I've been working on for the past 3 years in coordination with my team called Lit Protocol. And what Lit functionally is a key management network. The way we think about the era that we're living in, and certainly as Web3 developers and entrepreneurs and product people, we are probably more in this era than other people, but in the era where we want to consume services, not from centralized service providers, but from fault tolerant and programmable networks. Just heard some really excellent examples of this. And so if you think about this kind of large frame of where we're at in this network era, the way we think about it is blockchains like Ethereum, things like IPFS and Filecoin and Ceramic building on top of them, the data network, and then what we're building is the key management network, essentially the distributed programmable fault tolerant version of something like Amazon AMS. And so the primary question here is, why do we need a key management network? And this is something that I'm sure most folks in this room have experienced, which is doing key management is a cumbersome and complex process, whether we're talking about secret management for the back end of an application, or in the context of a retail user, or in the context of doing something like issuing a verifiable credential. And so just for the historical view here, in terms of how we got to key management, and this will dovetail into the makeup and the architecture of this network, let's meet the following three people: Adi Shamir, Andrew Yao, and Lisa Su. And as you can see, I've got the three specific technologies called out that these individuals are associated with, which is secret sharing in a threshold-oriented way, multi-party computation, and secure encrypted virtualization. And these are the primary technologies that make Lit. We can take a look at the network overview, but functionally, the security model here is to take a key and divide it up into a bunch of parts. In our case, this is 30 different parts represented by 30 different node operators. And then there is a threshold, which is to say that in order to generate some signature to sign a transaction, to decrypt some data with that underlying distributed key, 20 of those 30 parts are needed. Now, it does present a pretty interesting challenge, which is as nodes leave the network over time and new nodes join, how do you keep those old nodes from getting access to that underlying key share, that private key material, which is so important to keep private? And so the technology being used there is something called AMD SED SMP. We have plans to integrate with more types of TEEs, but this is essentially a cryptographically attested to black box. And so each node operator is essentially raising their hand and saying, here is the code that I am running. And then the other node operators will only interface with a node operator that can produce that valid attestation. And then so as you can see here, what this provides to developers, now that we have an understanding of the architecture, a key management service provided by a network, is an SDK that, here's some of the node operators, is an SD, we can look at this for a second, but then is an SDK that basically lets developers use this underlying key. So a pretty obvious example would be like creating a wallet for a user where they've got something like Google or SMS or Apple Passkey hooked up as the authentication method. Seen some really interesting things built around multi-factor authentication. Then one other thing to add is that on each of these nodes, they're each running a JavaScript execution environment. So developers can articulate sophisticated logic about where, when, and how they want this distributed key to sign. Essentially, you could think about this if you're familiar with Lambda functions from AWS or Cloudflare serverless functions. It's basically the same type of thing here, where you can write the logic, except the difference here is that that logic can be immutable, and the output of it can be a signature from the underlying distributed key. And then, of course, we talked a little bit about encryption. And some of the really popular use cases that I think are very relevant to this group are things like encrypting user data and being able to set rules around who can decrypt it, what they call selective disclosure. But it's been super fascinating because there's just a really wide variety of things that are possible here, from private data to user onboarding to bridges to private oracles. We've seen a lot of that stuff across the board. And so, just talk a little bit about data a bit more as it relates to the use of this system with systems like Filecoin and IPFS and Ceramic. The main use case that we're seeing there is applications that want to encrypt some data and then create a rule around who can decrypt that data. And essentially, what's so exciting about this is an example like Alice can encrypt some data and basically say, only people who have my NFT or only people on this dynamic registry can decrypt this data. And so let's say Bob is somebody who has access based on that rule set. Bob can sign a message. He independently connects to these 30 lit nodes. Each of these nodes independently verify, does Bob in fact meet the conditions for accessing this data? And then in a mental model similar to torrenting, Bob is then collecting these authorizations from these independent nodes and collects those authorizations client side on his computer. And when he's collected enough of them, he basically has the signature and can perform the decryption. And so this is a very unique thing where Alice can encrypt client side, Bob can decrypt client side. They did not have to be online or interact with each other in any way. However, there's no intermediary that was ever able to access the data throughout this process because the key provisioning was done through the distributed system. And then the last thing I want to mention is an experimental product that we're just starting to roll out to see if there's anybody in this room that's interested in. We're trying to find the first 4 or 5 groups to work with on this. It's a product we call domain wallets. I'm not sure if you can see it on the screen here, but the concept is to basically take a given TLD or a URL, so like Nike.com, game.gg, whatever, and then turn a subdomain, which would be a first name like alice.game.com, into something that both works like a crypto domain, which we all have a bunch of familiarity with, where you can send funds to that name, but the next level of this is actually imbuing a key, the distributed key, into that domain. And essentially, the hypothesis that we have is what interaction in Web3 can look like from an account-based view moving forward. It's for people that are not interested in self-custody or are on the path of progressive self-custody and want easier ways to access decentralized data and digital assets. Functionally, what we're talking about is individuals essentially logging into the username. So using like Google, Passkey, SMS, etc., to log into alice.game.gg. And then because that name is also associated with the distributed key, the signature to sign into the DApp or execute the transaction happens from there. And naturally, of course, this account name is represented as an NFT. Anyway, I know it's lunchtime. This was a super quick overview. I'll go back to the slide just for a second to see if there's any questions. But I'm very reachable. I'm David at litprotocol.com on email and at David L. Snyder on Twitter and Telegram. If there's a conversation that we should have that we can't have right now. Thanks for your attention. Any questions?
Yeah, is there latency associated with aggregating like 20 of those to actually create to sign something for the PC aspect of things?
Yeah, so this is a question like how does signing work basically?
Right.
Yeah, so let's say we call them PKPs, a programmable key pair. And let's say for the sake of example, you've hooked up Google as the authentication method, and you want to send 5 USDC to me. So there's some DApp, you log into Google, 20 of those 30 nodes independently validate that. And then you put an action, send 5 USD to David.eth, for example. And then those nodes basically check the authentication material. We have like session keys and stuff to make the UX on page more sophisticated so you don't have to sign again. But functionally, what's happening there is each of those independent nodes in the enclave is producing something called a signing share. So with this, their underlying part of the distributed key, they are basically, essentially what they're doing is signing the transaction, but they don't have the full key. And so they send their
It's
part.
similar to Taurus and Lilian, but then I'm just thinking the more nodes you have, doesn't that add complexity to the latency of aggregating that signing?
That's absolutely right. Yeah. So we kind of have it set at a 30 node network to start. And then there's some interesting kind of academic things in terms of expanding that. But the other constraint actually is the number of concurrent connections that can be made from the browser. So there's performance constraints and browser constraints on that. And where we see the future going because of those constraints, is less around having 10,000 nodes share the same key, but a similar setup to what they've done over at the Internet Computer with this subnets, and basically subnets having different flavors. So one of the subnets that we're really interested in launching next year is one that runs NVIDIA GPUs, such that you could run LLMs on top of this distributed key. So cool.
Yeah,
Awesome.
that's really cool.
Amazing. Let's cook, and then let's eat.
Thank you.